Electrolytes, something that is vitally important for the body. We have to figure out, though, is why are they vitally important? And we'll start looking at sodium as one of the electrolytes. Electrolytes. Pretty much an electrolyte is going to be a substance formed from ionic bonds that can dissolve into anions and cations. Anions, negative charge, cations, positive charge. So take salt, sodium chloride, NaCl, Na sodium positive, Cl chloride negative. Now, these components of the body are going to be found from head to toe. They have numerous different important processes to occur in our body. I mean, you can even argue they're the most important components of our body. How so? Well, do you like having your heart beating? Because you need sodium and potassium, two different electrolytes, to make sure the muscles contract. How about your brain functioning? The brain needs sodium and potassium again for electrical impulses. But all of these are regulated in a very careful and very precise manner, because any of these electrolytes can't get too far out of balance or your body will start to feel it very quickly. The ranges quite often are very narrow, so your body is constantly watching and monitoring and trying to make sure you can keep these all in a proper and homeostatic balance. Now, that balance might be a little bit unusual because some of these electrolytes, their balance is when they're actually out of balance. What I mean by that is the sodium, for example. It's kept in a high concentration outside the cell while being in a low concentration inside the cell. And that's how it should be. That's how your body keeps it in balance, by keeping it out of balance. It works. But it happens with several other of the electrolytes as well. So not all of them are balanced perfectly evenly between both sides of that membrane. So that's using that semipermeable membrane to make sure you keep the high and low concentrations. Now, that's occurring in case of sodium because of the sodium-potassium ATPase, or sodium-potassium pump. It's going to utilize energy, ATP, to push the sodium outside the cell against its concentration gradient. But it also does that for potassium. The only difference is potassium has a higher concentration inside the cell, which means that sodium-potassium pump is going to be pushing potassium into the cell to create a higher gradient. Now, all these gradients are having stored energy, stored potential energy. So when channels do open up, allowing those different electrolytes to flow, that potential energy allows them to flow down their concentration gradient. And that can help to generate electrical potential also. Because your body really is a battery. Your neurons, your muscle cells, they're all allowing small, very small electrical charges to travel. Just these little potentials. Now, this is nothing like you plug in something in a wall outlet, nothing like that. But there are very subtle charges that can be measured. If you've ever seen or had an EKG or ECG, electrocardiogram, that's measuring the electrical potential of the heart as it beats. That's sodium. That's your electrolytes working, helping the heartbeat. And they're measuring the electricity, that little potential that's across the membrane of the cells in the heart. So those electrolytes, kind of important to keep them in balance, or should I say out of balance. Either way, keep them so it's all set across the membrane with proper gradients if necessary. All right, let's look at sodium. Look at the first of the main. We'll get to potassium and chloride a little later. Sodium atomic symbol Na. You're saying Na, well, it's called natrium, is the original term there. So the original Latin term for sodium was natrium. It kind of stuck around, so they use Na as the term. Sodium is a positive charge, which means it's a cation. It's going to have a high concentration outside of the cell membrane and a lower concentration inside the cell membrane. And that's all maintained because of that ATP ACE or the ATP pump. Now, that gradient is going to help create a slight voltage charge or a potential charge across the membrane. We'll come back to that. But sodium also is going to help with fluid balance. Why? Because water follows salt. Water follows sodium. So if you increase the amount of sodium, your body's going to want to retain more water. That's why a lot of times very high in salt foods, if you ever had maybe one of those big soft pretzels loaded with salt, and then what happened after? You're probably pretty thirsty. That was your body saying, this is a lot of salt. I need some water to help dilute it back to normal levels. Water follows salt. But now, if you put all this salt into the blood, the water follows it in the blood. What happens to blood pressure? It goes up. So that's why we're looking at possibly hypertension as an issue from salt regulation. All right, salt, sodium specifically, can also help with nutrient transport. Now, this is based off of co-transports quite often. So sodium has already been having the energy put into its gradient. So it's high on the outside, low concentration inside. So when it goes down its concentration gradient, it can kind of pull things along with it. Sodium can have a co-transport with glucose. It can help to pull glucose into the cell. Well, that's a good thing considering the small intestines, even with high amounts of glucose in there, the small intestines still has lower glucose concentration than the cells, which means you're kind of pulling glucose into a higher concentration. Sodium can also help with amino acid transport. Again, the whole co-transport mechanism. And of course, I've already mentioned water. Yes, the nutrient water. Salt, water follows salt, works out perfectly. So moving all these things because of your salt concentrations. All right, nerve impulses. Kind of mentioned this already a little bit. Let's dig into it a little more. Your nerve impulses, whether it be on your nervous tissue, neurons, brain, spinal cord, or in your muscular tissue, heart, muscles in your arms, legs, your intestines, both those tissues can conduct electrical impulses. Now, we'll just use the neuron as the example. It's just simpler to talk about. The neuron itself will have high sodium outside, low sodium concentration inside. And also that means potassium, high concentration inside, low concentration outside. So the way this works is when your neuron receives a stimulus, it can then convert that stimulus into a signal, an action potential. Once that action potential starts, sodium is allowed to rush into the cell, into the neuron. Because it goes from its high to low concentration inside, that means that now you have a increasing concentration inside the cell. Well, your cell doesn't want that high concentration there, so it heads on down. The sodium molecules move down the neuron, and they keep triggering more and more of these sodium channels to open. It's just basically a constant influx of sodium coming in and moving down. That's referred to as depolarization. So when your neuron depolarizes, it's the sodium rushing in, and that's causing a change in the potential or the voltage. You can actually see it on a graph as going up towards the positive. But that's going to then go to the end of the neuron, release a neurotransmitter, and trigger the next cell. Maybe a muscle, maybe another neuron, maybe an organ, whatever it is, it's going to send that impulse into the next cell via a neurotransmitter. Now, we can't forget about the potassium I mentioned already. I know we're focusing on sodium here, but you've got to reset that cell. Put that potential back the way it was. So you have what's called repolarization. Repolarization is the potassium flowing out of the cell. Potassium has a high concentration inside, low concentration outside. So potassium flows out, all those positive charges are leaving, the inside of the cell goes back down to its negative state. You've reset the electrical charge. One of the many reasons why sodium and potassium are so important. They're helping with your electrical signals of your neurons. Now, if we take these and look at some problems, let's look at, for example, sodium, if there's not enough. So too little sodium dissolved in solution in your body is referred to as hyponatremia. Hypo meaning low, natremia, sodium. In the case of hyponatremia, you're below 135 milliequivalents per liter. Normal range is 135 to 145 milliequivalents per liter. So if you're too low, below that 135, your symptoms, now let's think, we're having now not enough sodium. So symptoms could be the fate of headaches. It could be a fate of confusion. You're looking at restlessness, weakness, even nausea, all because of low sodium. Well, does that make sense? Let's think. Confusion. Yeah, sure. The neurons aren't working properly. Brain's not working. How about weakness of the muscles? Sure, the muscles can't get the signals. How about headaches? Yeah, the brain's not firing properly. Nausea? You're not balancing everything across the membranes. So this is all based on low sodium. Now, in our society, for the United States, low sodium typically doesn't occur because of how much sodium is in the diets. Instead, it's a lot of times more common to see in the flip side, hypernatremia. Hyper meaning high. Hypernatremia. Now you've gone above the 145 milliequivalents. In this case, we're looking at extreme thirst, looking at confusion, looking at weakness, lethargy, restlessness. Hold on, weren't those the same symptoms as the other one? True, but the biggest difference here was the extreme thirst. Because with too much salt, you want to drink more water to dilute it. So we have hyper and hypo, too much and too little. You got to maintain that one little range, that 135 to 145 milliequivalents per liter. And your body actually is pretty good at doing that as long as you balance your diet, as long as you have adequate nutrients, adequate water intake. So the National Academy of Medicine posted what's called an adequate intake amount, called basically an AI. It's how much is recommended to ingest on a daily basis. For sodium, that's 1,500 milligrams in a day. That's 2/3 of a teaspoon. It's not a lot. If you look at the Heart Association, they claim 12 to 1,300 milligrams per day. So depending on where you look, the ranges do vary a little bit. But regardless, 2/3 or a little less than 2/3 of a teaspoon, that's not much compared to what we have in our diets. Most of the salt you ingest comes from processed foods. Now, in a lot of the more Western civilizations, like the US, for example, very fast-paced. A lot of times prepared foods are just simpler, faster, easier, grab and go. But that's not always the healthiest and most nutritious way. Preparing your own foods, not having them be pre-prepared, be processed and packaged, that's a way to help decrease the amount of sodium in your diet. And now, why is too much sodium a problem? We just went through all the problems there of hypernatremia. But don't forget, we also mentioned water follows salt. So if you have a higher amount of salt in your blood, you get more water in your blood, which they're doing research and it's looking like they're concluding that more water in blood, higher blood pressure, and higher blood pressure has a whole series of problems that are associated with it. So sodium, one of the 3 main electrolytes, because it has so many important traits to it. Until next time.